Hello, my name is Liz Arnold, and I'm doing a presentation on unsupervised learning of spoken language with visual context, which means natural language learning by associating words with objects. This was done by researchers at MIT at the Computer Science and Artificial Intelligence Laboratory. This paper presents a deep neural network model capable of rudimentary spoken language acquisition using untranscribed audio training data. Whose only supervision comes in the form of contextually relevant visual images. Normally, systems are highly supervised, meaning they employ a lot of pre-existing data and knowledge. Um, so as you can see on the slide here, the question proposed by the researchers was, can a computer learn a language through speech instead of text? Kind of like how humans learn. Problem statement in the paper is that current speech recognition technology, such as Google Speech API, uses large amount of expert knowledge and training data. This research was about speech recognition with little expert knowledge that works solely with images and speech. The sensor-based learning would allow a machine to acquire language by observation and interaction and could be applied to any language universally, probably in the future. This one was just with the English language. Some pre-existing work based on the paper was based on some previous progress has been made in learning language solely from untranscribed audio data. An example was segmental dynamic time warping, is a related discovery that enabled the repetitions of the same word like units in an untranscribed audio stream. Another similar precedent is a study that attempted to associate individual words from read spoken captions to relevant regions and images. Data collection, a new data set had to be developed since previous data sets with images have captions in text form. A new data set had to be made with audio captions. To collect audio captions, Amazon's Mechanical Turk was commissioned. This is an online service that allows requesters to post human intelligence tasks which can be solved by anyone for a reward, so like an open source online challenge. To collect audio data, users were presented with 4 random images. The user is instructed to record a free-form spoken caption for each image describing the salient objects in the scene. The backend sends the audio off to the Google Speech Recognition Service, which returns a text hypothesis of the words spoken. To get an idea of the error rates offered by the Google Recognizer, they manually transcribed 100 randomly selected captions and found that the Google transcriptions had an estimated word error rate of 23.72%, indicating that the transcriptions are somewhat erroneous but generally reliable. Here's just a graphic of how all the data was collected. The neural network calculates a similarity score for any given image and caption pair, where the score should be high if the caption is relevant to the image and low otherwise. The architecture of the audio-visual neural network with the embedding dimension denoted by D and the caption length by L. Separate branches of the network model, the image and the audio spectrogram, are subsequently tied together at the top level with a dot product node which calculates a similarity score for any given image and audio caption pair. So that's why there's the 2 separate branches and they come together with the dot product. Finally processing the results by taking the dot product of an image embedding vector with an audio caption embedding vector, it obtains a similarity score called S. Validation set of 1,000 image caption pairs from the testing set were used in the experiment for the paper. To perform image search given a caption, the caption is kept fixed and used the model to compute the similarity score between the caption and each of the 1,000 images in the validation set. So here's an example of what they used, some graphics. There was the audio data on the right there, and then that's the image that they would use. This is when the people would describe it, what the gray stuff is. In the majority of cases, the regions of the spectrogram which have the highest similarity to the accompanying image turn out to be highly informative words or phrases, often making explicit references to the salient objects in the image scenes. This suggests that the network is in fact learning to recognize audio patterns consistent with words using zero linguistic supervision whatsoever, and perhaps even more impressively is able to learn their semantics. Just more about the results. Overall, the network did not rely on any form of conventional speech recognition, text transcriptions, or expert linguistic knowledge, but it was able to learn to recognize semantically meaningful words and phrases at the spectral feature level. This differs from conventional image searching and speech functions because there's no text processing between the functions. And overall, this process is very similar to how humans learn language. Since humans kind of learn, to look at an object and associate the spoken word with it. It's kind of more a natural, or at least the human way that it's learning. Some potential future uses for this discovery. One long-term idea would be to collect spoken captions for the same set of images across multiple languages and then train a network to learn words across each of the languages. Another long-term idea would be to train networks capable of synthesizing spoken captions for an arbitrary image, or alternatively synthesizing images given a spoken description.